Good evening, ma'am. Can you able to hear me?
Yeah, go on.
Good evening, everyone. It's my pleasure to introduce Ms.Tharini Suresh, a passionate researcher and a technologist currently pursuing a PhD at Colorado State University. She is also a graduate research assistant at Epic Labs and serves as a research computing analyst in a division of information technology at CSU, where she contributes in analyzing and high performance computing initiatives. Before beginning her doctoral journey, Ms. Tharini Suresh gained a valuable industry experience at assistant engineer at Tata Consultancy Services, where she developed strong technical and analytical skills working on a large-scale technology solutions. Technically, Ms. Tharini Suresh is skilled in tools and platforms such as Python, MATLAB, and Cadence, Verilog, and TensorFlow and a hands-on experience in digital circuit and VLSI design as well as high-performance computing applications. Our research primarily focus on the interesting on VLSI designs and photonics and exploring areas such as micro or ring resonator, optical amplifiers, asynchronous circuit designs, while also integrating machine learning techniques into a hardware optimization. Once again, let us warmly welcome Ms. Tharini Suresh to the session. Welcome you, ma'am.
Yes, thank you. Yes, I'm just trying to share my screen. Mm,
Yes, ma'am. Now you can share, ma'am.
okay, yeah, okay, okay. Thank you for that very warm welcome, Srinidhi. Yeah, so I'll just get started. So today, as she already mentioned, my name is Tharini, and today I'm going to be giving a talk on generative AI acceleration with silicon photonics. I'm a second year PhD student at Colorado State University, and my current research interest lies in the hardware software co design of silicon photonic AI accelerators. Well, today's AI models contain billions to even trillions of parameters. With the recent explosion in compute and energy demands, particularly from the generative AI models, there is a need to accelerate them in a sustainable manner. Today, we will explore two classes of popular generative AI models, namely generative adversarial neural networks, which is GANs, and diffusion models, and discuss how silicon photonics can play a transformative role in accelerating these models efficiently. GANs and diffusion models have revolutionized AI by generating highly realistic synthetic data from limited data sets, addressing key challenges in data scarce fields. In medical imaging, these models can generate synthetic scans to add to training datasets and improve diagnostic performance. They also play a crucial role in 3D object generation as well as autonomous driving for generating training data. They are also used to generate synthetic faces for training facial recognition models. Let us now jump into how these models work. A GAN consists of two neural networks, the generator and the discriminator. The generator uses transposed convolutions, also known as upsampling, to turn random noise into high-dimensional data, such as images, while the discriminator employs convolutional layers to downsample and classify inputs as real or synthetic. The generator and the discriminator engage in a competitive training process called adversarial training. After training, only the generator is used to produce synthetic data, while the discriminator is not used during inference. So there are many different types of GANs that are used today. For example, Deep Convolutional GAN or DC GAN is a foundational GAN architecture that can be used to generate high-quality images. Conditional GANs enhance the flexibility of generative models by conditioning the generation process on additional information such as class labels, allowing for targeted and controlled image synthesis. Art GANs are specialized GANs designed to generate artistic and abstract images. Cycle GANs consists of 2 generators and 2 discriminators and are used for image-to-image translation. Apart from these models that we have seen so far, specialized GANs also exist for super resolution transformations, video generation, and style transfer tasks. So now let's get a basic understanding of how diffusion models work. They operate via a two-stage process. In the forward diffusion process, Gaussian noise is progressively added to a data sample over a number of time steps. In the reverse diffusion process, less noisier samples are generated at each time step. During inference, the model starts from random noise and iteratively applies this reverse process again and again to generate a high quality sample. This is called denoising. So in order to do this denoising, typically diffusion models use a unit structure, and it consists of stacked downsampling or encoder blocks and upsampling or decoder blocks with skip connections to combine low-level and high-level features for precise image reconstruction. The unit starts from random noise and iteratively denoises it to produce an image. Just to break down what the layers inside each of these blocks look like, you can see that in the downsampling path, there's convolution, normalization, activation layers along with multi-head attention layers. And in the upsampling path, we have these transposed convolution layers. So let's just have a basic understanding of what are what are the computations that happen within a multi-head attention layer. It consists of multiple attention heads, and inside each head, the input feature map X is multiplied with query, key, and value weight matrices to obtain the query, key, and value vectors. The attention score is then computed using these vectors. The output of all the self-attention heads are then concatenated and passed through a linear layer to obtain the final MHA output. The MHA layers help these diffusion models to capture diverse relationships in data. However, as you can see, they are computationally intensive. So coming into the different types of diffusion models that exists, starting with DDPM, it's a foundational diffusion model that learns to denoise images step by step from pure Gaussian noise. This is an example of DDPM with CIFAR 10 dataset. Moving to latent diffusion models, it compresses data into a smaller latent space to perform diffusion efficiently with a reduced amount of computation. And coming to the most popular type of diffusion model that is used today is it is the stable diffusion model, and it is very popular for its ability to generate high quality images or data, and it also has the ability to do text to image generation. For example, if I put in a prompt saying I want an astronaut riding a horse, it would give me an image like this. So let us now understand what are the challenges in accelerating these GANs and diffusion models. They pose significant challenges for traditional electronic accelerators. The transpose convolutions that we saw are part of the upsampling layers in the GANs as well as the upsampling blocks in the diffusion models. It involves inserting zeros into the input feature map before applying a kernel over it. This leads to inefficient computations and resource underutilization. These models can be huge with a large number of parameters that need to be accessed and operated on. Operations such as batch normalization in GANs as well as instance normalization and multi-head attention layers in diffusion models require frequent memory access, which causes bandwidth limitations and increased energy consumption. So a unified accelerator for these generative AI models should be able to flexibly adapt to the diverse structures of GANs as well as diffusion models, and as they each have their own unique data flows and layer compositions. So let's look at what are the prior efforts to accelerate these models. Initially, there was a lot of, there's always a lot of ongoing effort to optimize specific layers or operations within these models. Although these approaches have demonstrated potential, they each possess limitations that impede their scalability and efficiency. General purpose accelerators such as GPUs and CPUs suffer from substantial energy and performance penalties. As electronic accelerators face inherent limitations in the post-Moore era, several non-general purpose computation solutions such as FPGA, ReRAM, and TPU have been used to develop GAN and diffusion model accelerators. However, they each face limitations in terms of computational throughput and reliability issues as well as area overhead. So silicon photonics has recently emerged as a groundbreaking solution to the limitations of conventional electronic architectures. It uses light to transmit and process data, enabling much faster speeds than electrical signals. Optical interconnects in data centers provide faster data transfer and higher bandwidth, solving significant bandwidth and energy issues faced by traditional metallic wires. Silicon photonics integrates electronic and optical components onto a single chip, reducing size and power while supporting CMOS compatibility. Operating at the speed of light, it offers extremely high throughput. It delivers high-speed performance with very low power consumption, addressing energy bottlenecks associated with traditional electronics. It can perform complex tasks like matrix operations efficiently, making it a promising solution for computationally intensive applications. Prior works have demonstrated that silicon photonics can efficiently accelerate deep neural networks. So let us now delve into the fundamental devices and circuits that are required for computing with silicon photonics. Lasers generate the optical signals needed for computation and communication. Lasers can be on-chip, such as vertical cavity surface emission lasers or VCSELs, or the lasers can be off-chip. Waveguides carry the optical signals generated by the laser source. Using wavelength division multiplexing, a single waveguide can support multiple wavelengths. A microring resonator, or MR, is a compact optical device constructed using a ring-shaped waveguide. Each microring can be specifically designed and adjusted to work at a particular wavelength, known as the MR resonant wavelength. Microrings function as optical modulators that can perform multiply and accumulate operations by modulating input signals onto their resonant wavelength. MR banks consist of a group of microrings that share a single waveguide. Digital to analog converters are used to convert parameters from the digital to analog domain for tuning these microrings inside the MR banks that we are looking at. Sorry, just a second. Phase change material couplers or PCMCs leverage phase change materials which can switch between two states, amorphous and crystalline, with distinct optical properties. This allows them to dynamically route optical signals between different blocks in photonic circuits. Photodetectors are used to detect processed optical signals and convert them into analog signals. Analog to digital converters are used to convert analog signals to the digital domain for intermediate processing. So let us now understand how we can perform these multiply and accumulate operations that are a major part of our ML models today using photonics. So in many silicon photonic systems, computations are executed by modifying the wavelength of a microring resonator, resulting in a predictable change in the amplitude of the optical signal's wavelength. Summation is realized via coherent photonic summation, where optical signals with the same wavelength undergo constructive interference, resulting in the addition of their values. For example, to add A1 and A2, the first value A1 is imprinted onto the signal using the first VCSEL. The second VCSEL produces a value of 1, and A2 is imprinted onto the signal using a microring. When these two signals meet, their fields interfere constructively, yielding a new signal representing A1 and A2. Multiplications, on the other hand, leverage multiple optical wavelengths that are directed through MR banks. To multiply two input activations, A1 and A2, with weights W1 and W2, we first generate two signals with the value of 1 and mux them into a single waveguide. As they pass through the first MR bank, the first signal is modulated with A1 and the second optical signal is modulated with A2. The second microring bank imprints the corresponding weight values W1 and W2 onto the same optical signals, resulting in a multiplication operation. Now that we have a basic overview of how we can compute using photonics, I'm going to jump into our recent works where we presented a reconfigurable, sustainable hardware accelerator for GANs and diffusion models by leveraging silicon photonics. It is capable of accelerating the inference of a broad family of GANs and diffusion models. We have adopted hardware-software co-design approaches unique to each model. Our proposed accelerator demonstrates significant enhancements in energy efficiency and performance when compared to state-of-the-art GAN and diffusion model accelerators. So here is an overview of the proposed accelerator architecture. The design consists of dense, convolutional and normalization blocks, activation blocks, and multi-head attention blocks. Each block consists of multiple replicated units. So PCMCs are utilized inside the architecture for the dynamic routing of optical signals between these blocks. An integrated electronic control unit performs tasks such as interfacing with the main memory, buffering intermediate results, and mapping matrices to the photonic domain. Matrix vector multiplications inside the dense, convolution, and multi-head attention blocks are performed using MR bank arrays.
Hey, participants, please unmute your. Participants, please mute, ma'am.
I'm sorry, I'm just hearing some.
Yes, ma'am. Yes, ma'am.
Yeah, okay. So let us now see, we now have an overview of this accelerator, and we need to understand how it can be configured for GANs as well as diffusion models. The GAN configuration, as you can see, consists of dense, convolution, normalization, and activation blocks. The output of this dense block can be routed to the ECU or to the convolution block, depending on the layers that are present within the GAN architecture. And this convolution block can be optimized to handle both convolution and transposed convolution operations. Similarly, this is the data flow diagram for the diffusion model configuration. The proposed hardware also is able to efficiently accelerate a broad family of diffusion models. Yes. So let us now break down what each of these units inside these blocks look like. So the dense unit is photonically implemented using two microring banks, with one bank tuned to the activations, to the input activations, and the other bank tuned to the weights. Modulated optical signals are then detected by balanced photodetectors. For adding the bias values, coherent summation is used. So in a similar manner, each convolution unit is photonically implemented using two MR banks, one for activations and the other one for weights. So the normalization unit is implemented using broadband microrings, and it can support batch normalization as well as instance normalization. So what this would do is it would kind of project a value onto all the onto all the waveguides. And each normalization unit includes a mechanism to bypass broadband MRs. And with this mechanism, we can skip this normalization operation if it's not present in the layers of the GAN or the diffusion model. So prior works, coming to how the activation unit is implemented, prior works have demonstrated that semiconductor optical amplifiers can be used to implement nonlinear functions such as sigmoid, ReLU, and tanh optically. The leaky ReLU activation function is commonly used in GANs, and we implement it photonically using semiconductor optical amplifiers. First, a comparator circuit is used to determine the polarity of the input signal. The output of the comparator circuit controls a PCMC switch. If the input to the leaky ReLU block is positive, it is routed to an SOA tuned to 1. And if it is negative, the signal is fed to an SOA tuned to a small value A. In a similar manner, this is leaky ReLU is for GANs, but in a similar manner, diffusion models have a very specific activation function that they use called swish. And we have also proposed the photonic implementation of that. Let's now understand how we know from prior slides that within each attention head inside a MHA layer, we need to compute the query key and value vectors as well as the attention matrix as well as the attention score. The first part of this computation is called the attention matrix. So using a decomposition strategy, q.kd can be q.k power t can be written as shown in the slide. So in the MHA unit, this is performed using 4 MR banks, and using these balanced photo detectors, the results are accumulated and sent to the ECU for processing the softmax values. In parallel, the value matrix is generated using MR banks in the lower row, and the attention matrix values that are calculated after softmax are used to modulate the MRs in this MR bank. And in this method, we are able to get the final attention head output. Okay. So now let us move to how we can adopt certain hardware software co-design methods inside this architecture. So we saw that transpose convolutions are common to both GANs as well as diffusion models. Zero insertion in transpose convolutions lead to underutilization of computation resources. For example, let us consider a 2 by 2 input feature map. So during transpose convolution, it is expanded to 5 by 5 after zero insertion. Then a 3 by 3 filter is convolved over patches of this expanded input to generate the final output feature map. As you can see, to generate the first element, only 1 out of 9 multiplications is needed. The rest of the multiplications are inefficient and lead to underutilization of computational resources. So how can we deal with this? To overcome this issue, we propose a sparse-aware data flow. We flatten this input feature map and identify the all zero columns in the flattened input feature map and the corresponding elements in the flattened kernel. These zero columns and their associated kernel elements are eliminated, resulting in a final reduced dot product operation when computing the first output element. This approach reduces redundant computations and conserves valuable computational resources. To maintain data integrity and correct output dimensions, the removed columns are dynamically reintroduced during the computation stage in the electronic control unit. So we also employ certain pipelining between these units that we just saw. So in the GAN configuration, pipelining is employed at 2 levels of granularity. The dense unit and its subsequent activation unit are pipelined together. The convolution unit is pipelined with both the normalization and activation units. Further, as you can see, the operations within dense are pipelined. We also employ power gating such that when the dense block is active, the convolution block is deactivated, and vice versa. By selectively powering components as needed, the GAN configuration minimizes energy wastes in idle parts. Additionally, this enables the sharing of DAC arrays, which are used to tune the microrings between the dense and convolution blocks. Similar optimization techniques were applied for the diffusion model configuration as well, but since that paper is currently under review, I'm not I haven't included it in these slides. So, coming to the experimental setup, we performed detailed analysis of the proposed accelerator using 4 GAN models, namely DC GAN, conditional GAN, art GAN, and cycle GAN, and 3 diffusion models, that is the denoising diffusion probabilistic model, the latent diffusion model, and the stable diffusion model. Using optoelectronic device models and layer-wise mapping of each model, we developed a Python simulator to evaluate the performance and energy costs of the accelerator. We applied 8-bit quantization to these models and evaluated them using the inception score metric. It is a metric that kind of helps understand how good of an image has this model generated. There are other metrics, but we chose the inception score metric. And we further compared them with state-of-the-art GPU, CPU, TPU, FPGA, and DRAM-based accelerators. So we one of the first experiments that we did is to perform a comprehensive architectural design space exploration to identify the configuration that maximizes GOPS per EPB, where GOPS is the giga operations per second and EPB is the energy per bit. The 4 key architectural parameters in the GAN configuration are N, the number of columns in each MR bank array, K, the number of rows in each MR bank array, L, the number of units in the dense block, and M, the number of units in the convolution and normalization blocks. For this analysis, we set a power limit of 100 watts, which aligns with our goal of creating an energy efficient GAN accelerator suitable for resource constrained environments. This design space exploration yielded the most optimal configuration for NKLM as 16, 2, 11, and 3. A similar exploration was performed for the diffusion model configuration as well. So we then conducted a sensitivity analysis to assess the impact of the proposed sparse computation data flow, pipelining, and power gating techniques for the GAN configuration. The baseline configuration, which does not incorporate any of these optimizations, serves as the normalizing point. And it was observed that on average, the combination of all 3 proposed optimizations reduced the energy consumption by a factor of 45.59. Similarly, for diffusion models, it was observed that on average, the combination of all 3 proposed optimizations reduced the energy consumption by a factor of 3. So moving to the GOPS for each model, we wanted to understand how much speed up or we are getting with the photonic accelerator. It is observed that the proposed Gen AI accelerator achieved at least 4.4 times higher GOPS compared to the state-of-the-art accelerators. The high GOPS performance is primarily due to its use of optical computations through silicon photonics, which offers high bandwidth and low latency, thus enabling efficient parallelism and rapid data processing. These advantages are further enhanced by our proposed data flow and scheduling optimizations. So then we also estimated the EPB for each model. It was observed that the proposed Gen AI accelerator achieves energy improvements of at least 2.18 times compared to state of the art. This EPB improvements can be attributed to the optical accelerator's low latency operations and energy efficient computational flow. In a similar way, we did the GOPS and EPB analysis for diffusion models, and we observed a 94 times higher GOPS compared to state of the art. And for the EPB for each model, it is observed that we were able to achieve at least 3 times lower EPB. And to conclude this talk, we have discussed the silicon photonic based AI accelerator that can accelerate the inference of a broad family of GANs and diffusion models. In comparison to general purpose computing platforms and several state of the art Gen AI accelerators, the photonic accelerator achieved at least 4.4 times higher throughput and 2.18 times better energy efficiency. These findings collectively highlight the significant potential of silicon photonics to deliver sustainable inference acceleration with significant energy improvements across a broad spectrum of Gen AI models. I would like to thank, that concludes my talk. I would like to thank Dr. Benilla as well as the rest of the organizing team at R.M.D. Engineering College for this opportunity. If anyone has any questions, I'll be happy to answer. Yes.
Hello, ma'am. I'm Dr. Ashutosh.
Yes.
Ma'am,
Hi.
we are working on a accelerator for image processing. The thing is that, see, we are able to make the software accelerator. The thing is that for hardware accelerator, how to find the problem is that we don't have advanced FPGA boards in our university. So I'm just looking for a option how to do implement on the hardware accelerator on a hardware, some hardware which is suitable for us. So basically, what we are doing trying to train a CNN network. So we are
Okay.
doing a customizable CNN network so that it basically suits our need.
Okay.
Okay, since it is based on image processing, the data size is more. So we are trying to
Okay.
reduce. We are doing that max pooling, all those things we are doing, so that the size of the images can be reduced. But what we are finding is difficult to implement on a FPGA board since our university don't have the advanced boards actually. So how to do that?
So have you done all the model compression techniques that you can?
Yeah, mostly we have done that, ma'am.
Okay. So sometimes you have these simulator codes available online in cases
Okay,
where you don't actually have the actual hardware in your hand. You can build your own, you can you can break down the flow inside this FPGA hardware and just get the latency and power values associated with each of these small stages inside inside the in the flow, in the data flow. Like you saw, like I had like a data flow diagram.
yeah, ma'am.
So in that I had kind of broken down how this each unit and there is a path associated with each unit. So when I'm writing suppose I don't have the actual hardware, what I do is I kind of get those numbers from prior works, or I have to simulate just a small part of that circuit to understand how much latency it would take overall. So you can like
Okay,
just build it using Python. So that
yes,
is
ma'am.
one way to go in case you don't have like the actual hardware, or sometimes you also have these existing models or existing simulator codes online. Like in some GitHub repos, I know that we have the ability to plug in like the ML model parameters and the sizes, and you can just kind of it will just give you an output of how much latency or how much energy it is consuming on that specific FPGA board
Okay,
without
ma'am.
actually doing the run. So that is one way to look at it.
Yes,
Or
ma'am.
just break it down into very small. So instead of looking at it as the entire board, just break it down into small units and understand how much latency is going to be involved in that part. And then you can map it to your entire architecture.
Okay, ma'am.
Does that make
One
sense?
more
Okay.
thing we have one more thing we are facing actually. See,
Okay.
normally what we are doing, whenever we are making any model on CNN, we're using a Python codes. So when we want to implement on a FPGA board, we have to convert that Python code to a Verilog code, and then we have to convert. Then only we can dump. So basically, what we have done, we have created a very basic serial network, and for that also, it's difficult, a tedious job to convert a Python code to a Verilog code and then implement in FPGA boards. So any other way is there for that one, so that we can directly dump a Python code to some FPGA board if you are able to find a suitable FPGA boards.
Well, I haven't worked with FPGA boards, Ashutosh. But one thing I can say is, in case you can always understand how the mapping would work and write it down.
Yeah, that is what
If
we're
you're
trying.
finding it
We are just
difficult, because I
no,
haven't
it
personally
is not
worked with
difficult.
Verilog.
It becomes more tedious actually.
Yes, I can
So
understand.
rewriting the same thing again in a different language, so it becomes more tedious actually.
Okay. So it happens.
Yes. Yes. Okay,
Yeah.
ma'am. Then,
Yeah. In case you're
I
not
heard
able
that
to, you can always
there are
get
some.
like a rough. Yes, sorry, please continue.
I heard that there are some edge devices which is available as edge device simulators are available. So, do you have any idea about that? But I heard, I have not used that one, but I heard, I try to find that alternative. I'm trying to we are trying to find the alternatives. So
So
that's
I
what.
have an idea with ReRAM, but I'm not very familiar with the FPGA part.
Okay, ma'am.
Yes, I'm sorry about that.
No problem.
Yeah.
Thank you so much.
Yeah, one thing you can do is like try to get those values from prior works. If any paper has reported latency values, that is definitely uh, a way to go about it.
Yes, ma'am.
Yeah,
Definitely, ma'am.
okay, sure.
Thank you, ma'am.
Thank you. Thank you. Uh,
Hello.
yes.
Hello, ma'am. This was a wonderful session. I have a question. How do AI accelerators balance high performance, specifically in low power consumptions, in edge devices, etc.?
Um, so yes, like I was just telling Ashutosh, so one thing like I mentioned, like we do quantization to make the
Okay.
model size as small as possible. And these days,
Okay.
like for all these, so normally we do quantization using TensorFlow.
Okay.
So you have like these post-training quantization methods, then you have pruning, then you have quantization aware training. So these are some methods
Okay.
that you can use to compress your models. And one thing I would like to mention here is that these GANs and DMs that we talked about, they each have their own customized quantization methods available. So,
Okay. Okay.
um, which is very tailored to these diffusion models and GANs, so that when you quantize, you don't lose too much of your image quality that is being generated by these models. And another way is so by doing this, the number of the model size reduces the one that you need to feed into your accelerator, and then then after you do that part inside the hardware, like normally how we try to parallelize operations, like with the photonic part, I explained how we are able to do multiple multiply and accumulate operations at a time in a single path. So specific to the hardware that you are looking at, like just trying to parallelize operations um, will help with your latency part.
Okay. Okay. Great. Great. Thank you.
Yeah. Okay.
Can I have one more question, please?
Sure.
Yeah. Ma'am, I have a very brief question that how can AI accelerators stay adaptable to rapidly changing our latest technology like AI models, specifically in transformers and beyond?
So that's the thing. Like all these models, they have like nice big. They have like these they have like different purposes. Like your transformers, they're able to respond to queries, and if you ask like ChatGPT something, it's able to tell you something fast. But when you break down the layers that you see within these models, you'll just see like 1 to 2 new layers apart from your very conventional, dense, convolutional normalization and activation layers. You'll see like these multi-head attention layers, like very few tweaks or certain new layers would have been introduced. So our existing AI accelerators can be used for all these conventional layers, and you would just need to think about, okay, so this layer is new. For example, this multi-head attention layer is new. So how can I accelerate that using my existing components? So if you saw, I had used MR banks for conv, norm, as well as I had used some, I had kind of just reused these MR banks to do those functions. So can I use my existing hardware to perform? How can I change the layout, or how can I change the configuration so that it will be able to accelerate these new layers? That is one way to think about it.
Thank you. Thank you.
Yeah, sure.
Thank you. Great. Thank you.
Sure. Thank you.
Tanya, I have a question for you.
Yes, sure, Dr. Benila.
Actually, you have proposed a sparse computation for the data set. Am I right?
Yes.
No. Have you worked the computation for any other computation for the data sets, and how you are saying that this works better?
Uh, yes, ma'am. So the thing with these existing works is that none of them, so these transpose convolutions inside which these zeros are inserted. So this is part of the software side, but most of the prior works, they didn't really look into into whether we can cut off this um, cut off feeding these zeros into our hardware, into our conventional CPUs or GPUs. How can we cut them off? And so that's why when I compared the work in the slides that I showed you, I can there was I can just go back just a second. So if you see here, this software optimized bar over here, this is one of the pipelining techniques that we employed, and that is what is the sparse computation data flow method. And then to our baseline model, when we applied all these three techniques together, we got a final optimized model. And then using that model, we compared to the existing state of the art that you can see here. So this is your GPU, CPU, TPU, FPGA-based accelerators, and ReRAM. So it just it they didn't really look into how can we not feed the zeros into the system. Is that clear, ma'am, or am I not
Yeah.
understanding your question?
Yeah. No, we worked using the sparse representation. We worked for images, long back. So
Okay,
that's why I thought, no, have you tried for any other computation? That's why I asked.
okay, mm, okay, ma'am. Yeah.
Thank you.
Mm.
Could you,
I'm
yeah, could you tell something more about your research, no, the extension of it, proposed work, anything?
Yes, ma'am. So this sustainable Gen AI accelerator. So the most recent work we did was trying to combine the works into one and understand whether the same accelerator can be reconfigured and used for DMs and for GANs and diffusion models. And right now we are kind of looking into neuromorphic computing using these using this photonic substrate that I showed. And apart from that, we have also proposed a paper that on a silicon photonic accelerator for just diffusion models. So that is some ongoing that is under review, and the neuromorphic computing is what I'm looking into right now. I'm seeing a question from Dr. P. Dr. Pattanarajam. What software are you using for optimization? Which software are you referring to? Um, so I use PyTorch to train these models. We have available repositories. We have available repositories for these models like StyleGAN and QDiffusion to help with these models. Uh, uh,
I think you have shared a feedback form for only session 1.
Ma'am, ma'am,
We have, ma'am, we have not received a session 2 feedback form, ma'am.
ma'am, still session is not completed, ma'am. It's up
So
to 9:30.
it's up to 9:30.
Yes, ma'am. Ma'am,
It's okay, ma'am.
ma'am, Tharini, ma'am.
yes.
Can you explain then how do AI accelerators differ from traditional process like CPU and GPU? Then in how we are handling in intelligent automation task, ma'am.
So with intelligent automation, are you asking from a VLSI perspective?
Not real first, ma'am, like CPUs and GPUs in handling intelligent automations.
Yes, just a second.
We are using them, ma'am, different how AI process that accelerators can be differ from the process are different, right, ma'am? Like CPUs and GPU.
So this part. So that is the. So I would just like to explain with this slide. So over here, GPUs and CPUs, they AI accelerators in one line, I can say that AI accelerators are more customized to deal with the different kind of computationally intensive layers that we saw within like ML models. CPUs and GPUs, though they are great, they are really good at for example, with GPUs, we can process a lot of data in parallel. However, it's not a very efficient way because, for example, if I'm feeding in a transpose convolution layer, it's going to end up doing a lot of those although a lot of those multiplications with zero that we spoke about. However, like these customized AI accelerators, they are more adept at handling any kind of inefficient computations or any computationally intensive layers better.
Okay,
Does
ma'am.
that answer your
Yes,
question,
yes,
ma'am?
ma'am.
Or
Yes, ma'am.
okay.
Yes, ma'am. So what are the design challenges you are facing, ma'am, while we are developing the efficient AI for the
Yes.
real-time applications? What are the challenges you are facing while developing, ma'am?
Uh, what are the real time challenges? So I can in the perspective of this of these models we looked at. One thing is understanding how these layers work, and just kind of understanding where these intensive MAC operations come from. And the challenges are having a nice balance between the latency or the time taken for inference, or in this case, to generate a really nice image, as well as the power behind generating this image. We need to keep it balanced. We can always have like a lot of these micro ring banks, um, and accelerate the generation process in a very we can get the image very fast. However, the power taken by that hardware to generate that image shouldn't be too high. So the challenge is like understanding where the latency and power consumption comes from, and finding a nice balance between them.
So how you are analyzing the power, mom, there? So while we are going for, as you told, you are not working with the FPGA. So how we are going to calculate the power analysis in that DRAM, ma'am, actually?
So I don't work with ReRAM, but I have the values from prior works. But the I think I in the so you are seeing these components that are being used to build the photonic accelerators. So each of these components, they have a latency value and a power value associated with them. So using those small values, like I was mentioning to Ashutosh, we can slowly build up, since we know the value for each component, we can build up the power consumption of that entire architecture using a simulator code.
Yes, ma'am,
And
through the cluster input, ma'am, or
sorry?
so how we are giving that simulated input to the power, ma'am, actually? Simulated, as you told, it is simulated. So it is given from that input side, or any other input you are given for power, ma'am?
So these DAC arrays that are used to convert the values from the digital to analog domain, those there is a power value associated with them, and there's a power value associated with these. Some of these components are active, and there's a power value associated with each of them inside the architecture.
Okay, ma'am. Can you give any real-time application, ma'am, relevant to this photonic AI? Any real-time application? That because we can take to the students for easy communication. So they one real stuff.
Yes. So you can use this accelerator in data centers, in which we run these models to make sure that they don't consume too much power. You can integrate them. I'm sorry, I seem to have. Yes. So you can integrate them inside these, um, inside like any data centers inside which these AI models are being deployed. In that way, we can reduce the power consumption of that center, as well as we can enable like a good. Uh, so suppose we Yes, so you can integrate these photonic integrated chips into existing data centers. So there are like companies today like Light Matter that are working on these photonic integrated chips, and they actually look at accelerating multiply and accumulate operations inside these AI models. So that is one example you can give them maybe for
Is
the real
relevant to
time.
okay, ma'am.
That,
For an automation, ma'am, in automation.
Yes, like definitely. So let's say you are using any kind of tool. At the background, there is an ML model. So those ML models can be deployed on these photonic chips. So
Can
you
you
kind of like
recommend the
offload. Yes, sorry, ma'am. Please continue.
ma'am. Can you recommend any learning and experimenting with AI design, ma'am? For framework tools or frameworks?
Yes, you can definitely start with TensorFlow. TensorFlow is a very nice tool for students to explore basic AI layers and play with them. And then you can transition to something like PyTorch. For basic AI models like CNN, RNN, TensorFlow is a very nice space. But for these models that we looked at for GANs, diffusion models, there are like PyTorch repositories like StyleGAN, um, Studio GAN, as well as Q Diffusion. These are some nice frameworks or websites to look at.
Oh, Ms. Tharini, there is a question in chat box. What are the latest trends in hardware, software, co-design for efficient AI accelerator development? Dr. Rajesh have asked this question.
Okay. Latest trends. Well, they are more focused on sustainable. I think the latest trends are more around sustainable AI accelerators, because the power consumption behind each ChatGPT prompt, for example, it's a transformer model. Each of these prompts, it's consuming like a lot of power, and sustainable AI acceleration is a very up and coming field where people try to understand what are the water requirements or the carbon footprints of these of developing AI hardware. And I'm seeing papers on photonic integrated chips as well. So that is a latest trend that is going on.
Hello. Hello.
Yes,
Hello,
hi
ma'am. Can
Srinidhi.
you hear me?
Yes.
Yeah, ma'am. I want to know about what are the emerging research gaps in AI hardware as well as in automation, ma'am?
I'm sorry, can you please repeat that? Your voice is kind of breaking.
What can you able to
Uh,
hello?
Type it in the chat bar if you have network issue.
Oh,
You can type your questions in the chat box too. What are the emerging research directions in AI, hardware acceleration, and automation?
well, so currently I'm looking at neuromorphic computing. So with the models that we have been looking at, all the data sets are in the full precision data sets. So what happens with these? So there are two emerging directions. One is like looking at neuromorphic computing, and the other one is sustainable computing, which I just mentioned. So for neuromorphic computing, all this input activations that I had shown in the optical computations part, those values are ones and zeros. It has been around for a long time, but since it's a very power efficient way of computing, it is like a very emerging field in AI hardware currently. And as mentioned, sustainable computing is also a way to look into, is definitely a very promising research direction, because people want to understand what would be the environmental impact on deploying such hardware.
Ma'am,
Yes, Priya.
ma'am, one more question, ma'am. So how you would differentiate this photonic chip design with traditional chip design, ma'am?
Differentiate in the sense, in which aspect are you asking, ma'am?
What impact it is going to be, because now we work with power, and we work with the area, and these are the performance, we work with speed. So once you are going for photonic, compared with the traditional chip design, what would be the difference, ma'am?
So I had shown like the throughput and the GOPS and EPB results. So area is also definitely a direction to look at. I haven't looked at it for till now. Um, One thing I would say is with the speed, there's definitely a higher speed as I had shown in my GOPS slides, because with one waveguide, we are able to do multiple operations at the same time. So using wavelength division multiplexing, we are in one pass, we are able to do multiple MAC operations at a time. So that definitely offers like a very high parallelization when we are doing these multiply and accumulate operations inside these AI models. And power wise, the component our prior our studies have demonstrated that the power requirements of these um, accelerators are definitely lower than existing electronic uh, conventional accelerators for like CPUs and GPUs, as well as any specific any customized electronic accelerator.
Okay, ma'am. Thank you, ma'am.
Yes. And since we are here, I would also like to mention that stochastic computing and in-memory computing are also some directions that are very that are looking very interesting to researchers today. So with in-memory computing, we don't need to move the data between your memory and your computing area. We can just using some small circuit modifications inside your DRAM or flash, we are able to do these MAC operations that we looked at in photonics using very simple electronic circuits like AND gates, or by cascading AND and OR gates. And another domain that is really interesting is the stochastic computing, where it's again representing input data as ones and zeros, but there is some randomness associated with it. So these are also some directions that I feel like mentioning at this point.
Okay, ma'am. Thank you, ma'am.
Yes.
Thank you, Ms. Tharini. Now I invite Ms. Sendil Priya to propose a vote of thanks for the session too.
So, good evening, everyone. So, on behalf of R&D Engineering College and the EC Department, I sincerely thanks Ms. Tharini Suresh, PhD scholar at Colorado State University, for her informative and inspiring session on AI for intelligent automation. Ma'am, thank you so much for your valuable insights into advanced concept of AI accelerator, ma'am, and their connection with modern computing. We are truly appreciate your time and effort in sharing your expertise with us, ma'am. Thank you so much for the enlightening session, ma'am. Thank you, ma'am.
Sure.